Hello, everybody. Thank you for this introduction. So the last year, I mainly work in the bridge domain, so you will see a lot of bridges, less buildings. And I'm quite honored to be here in the best conference over structure in the world. You know that? Yeah, everybody knows it. And I was intrigued by the title of the conference, Redefining the Art of Structural Design. It's quite complex when you think about it. And so I wondered myself, what did we do the last 30 years? Or what did we redefine in structural design? And if I have to say two things, I think it is one, what we name the integrated design. So trying to put several functions in one element, instead of having a lasagne of structural elements, layers of structural elements, to try to integrate a lot of function in one element. So this is something which is normal in other industries, but in our profession, it's really not common. So we have a very conservative approach. And this is one part of the things we did, going to an integrated design, to a sort of minimalism, a reduction of elements, a concentration, getting to a sort of coherence in the design. I think this is also important because we are building things for minimum 100 years, 200 years. I think the oldest bridges still in function today are over 1,000 years old. And when you think about sustainability in the bridge domain, I think it's really different from buildings. Bridges are something which remains in the landscape. Sometimes they are used in another way, but they remain, they are structuring our world. So this was one point, this condensation. And the other point was about form and forces. 2009, we made an exhibition called Shaping Forces. And the idea of this exhibition was that we should use the forces to find the form or to have a sort of dialogue between force and form. This was also uncommon in the bridge world. And it goes a little bit further than form finding, because in form finding there's a sort of passive role in the designer. I think we can have an active role. We can manipulate these forces. We can bring the design in a certain way, so defined by the border condition. Yes, and this was the second part of this reflection. I will start with a project which was a milestone in my career. It was in 2003. 2003, 20 years ago. We had rhino, we had not grasshopper. No. So it was another word, I think. When you look at this, what do you see? Or what should you see in a normal bridge? You should see two piers, solid, anchored in the ground, with two hangers on each side, a longitudinal beam, a transversal beam, having the abutments where you have a dilatation joint. That would be a normal bridge design. What do you see here? It's one surface, it is one plate. And this plate, it's cut out in a certain way. And if you take your finger, it's also about topology. If you take your finger and you are going around this line, This is an infinitive line going to the other way, etc., etc. So it's about surface, about plates, plates that are bended, plates that are cut out, plates that are folded. And these three themes of bending, folding, and cutting out, I want to show it on different projects because it's something which always comes back. We are working with plate material. It can be steel, it can be wood, but also in concrete, finally, we have to do formwork. So I think the problem remains the same. And I'm not an academic, I'm working in the real world. And we have to try to do the things with the contractor, yes, which really don't want to change anything. They are allergic to risk. So the first things they are doing is a risk analysis. But anyway, we have to go on. So we have to use the techniques they are used to, but in another way. So Knock was important, was a start, was a sort of milestone, a statement of how a bridge could be seen in another way. Also the way the bridge stands on the earth, instead of being clamped, it's very fragile, because we want to have a hinge there, rotation. But on the other hand, the abutments are rigid, it's an integral bridge. So we don't need to maintain it there. So it was another approach of bridge design. I like to make the comparison with other industry planes. There's 66 years between these two photos. Take two bridges, 66 years, they are looking the same. And here we are in another world. And the left picture is typical from this engineering thought of the 19th century. So you have a complex problem, and you are cutting this problem in simple problem, and you find solution for every simple problem. And then what is the design? The design is the result of adding again all this simple solution together. It's a sort of additive logic. The right side is something else. It's about optimization. It's about taking away material. It's a sort of subtractive logic compared to an additive logic. I like also the comparison with the planes, because when I see bridges, today there are a lot of bridges that don't fly. Think about it. But ultimately, the judge for a plane is to fly. In bridge, you are putting a bridge that weighs 2 times, 3 times, 4 times more. It still works. And I know examples of bridges that are 2 or 3 times heavier than needed. And maybe that's one point about sustainability also. Making a good design is the first step to sustainability. Well, from this additive logic to this subtractive logic, 1903, you understand, so the addition of the different elements, 1966, 60 years ago, so 69 was the first flight, so it's really impressive what happened. If I come back to Knock, we did sort of optimization. We defined the topology and make some holes, and we came to a sort of qualitative solution result where we know how to open it, how was the right height for the structure. Well, Is it new? Not really. We never invent, we reinvent. We redefine. This is an example of a spear 2,300 years old. It's one line with some opening. I don't know why the openings are there. Is it only decorative? Has it a magical effect? So natural? Has it a real effect? We don't know, but I think it's very beautiful, finally, to get to something so strong in the design with simple means. But structure normally are elements put together. So this is the mathematical bridge in Cambridge. And you see here's the problem we have, because in the forces we want continuity, but in reality we have to assemble. So we have a problem, a weak point there, or we have eccentricity, because two elements are crossing, or we have to stop one element and bring the effort to the other side. So the two options are not ideal. Here's another example with a lattice, a small bridge, very beautiful, finally. But when you look at the crossing, you have a problem, because you are taking away material, and you have this eccentricity you will deal with. You don't want these things. And this is, for me, an unsolvable problem. So the crossing of two lines. And it's very easy to draw two lines, but to materialize two lines and the crossing is something which is very complex. And the idea here was to say, okay, instead of trying to put two elements, we are working with a plate material, we are cutting out the material so that the flow of forces can pass from one to the other. And we did some bridges with this idea. In 2002, it was first one. So it was a plate lasered out. It's 26 meter span, and it is the railing which is the structure, the bearing structure. Other example of the same technology, and another example here in Bruges, which is a sort of hybrid between a Virendale and a diagonal-shaped truss. This crossing of two lines, we did also in another scale, Ingelmünster, 2008. And when you look at this, you have one plate in the middle, and you have two plates. And the effort is going from the one plate, the outside plate, to the web and going down. So there's continuity in the flow of forces. And finally, you come to another language. So this simple crossing, the expression becomes really different. Durability is also important, and you see here that the water flow is continuous, and these sort of things are very important for durability. Another way to deal with the crossing was in keel canopy. So instead of stopping one plate and continue, we bend it, we fold it, and we fixed it together. And you see the result here, and the fixation and the continuity of this strip line. We did the same principle in bridge in Tintagel a few years ago. And you see here that you have two bended elements with a fixation here. And this is interesting also because of the construction. This had to be made in different elements because we could only transport elements of 5 tons, over a cable crane because it was not possible to access the building site. Here are some photos from the erection of the bridge. It's very important in bridge to think about how you build it, and this has also a repercussion on the design, on the form of the bridge. Here you see these elements, and you see how they are connected. 5 tons placed with this cable crane, working about 50 meters height. Well, the finished bridge, and yeah, because yesterday also someone showed Kinshasa, so I thought I also put so approved by the landowner, so we were all happy because he had always an eye over our shoulder. But well, it's really well integrated, and that was really important, so that this bridge disappears in the landscape and not destroying this historical site. Well, another example of searching for another expression. It's a glass roof. It's Oosterried. It's in Antwerpen, and we were looking for changing this normal grit which we find always in glass roof, and it makes sense also here because it's Baroque. It's heritage. Protected, and this round form is a sort of modern echo of these Baroque forms which are present in the house. Well, it's 10 meters and 14, and for the engineers in the room, so we are going to 10 millimeters in the midsection and 35 millimeters in the corner. Well, same idea in a bridge in Antwerp, 2006, spans 67 meters. For me, a bridge starts at 30 meter span, so it's before is something else. You can do a lot of things, and then you have to do it with forces, with the efforts. So I think there's sort of symbolic limit. It's my limit. It's 100 feet. So. And when you look in the history, during 1,000 years, from the Romans to the Middle Ages, the maximum span was about this 100 feet. Well, the idea of this bridge was it's a sort of hybrid between a beam and a bowstring, but very flat, 1 to 30. We have no stiffener inside. It's one sheet of metal, again cut out, bended, and you have these openings inside. And when you are going from one side to the other, it's like you are going through a sort of tunnel, going from the city to the park. It's a transformer bridge, and when you look under the bridge, it's also very simple, some stiffener. Yes, there it was necessary, but in a very irregular way. The idea of this bridge was also to work on the texture, so I wanted to see the welding, so it's part of the texture. So instead of taking away all the material, you can take away a part of material also, and we see that on the side here, where you find the pattern again, but only taking away a few millimeters of steel. Well, some architects saw that, so they asked us to design a bridge in the UK with a similar idea. It's a smaller span, but with much more complex geometry in plan. And of course, in this type of structure, we are using form finding to get the right shape. Also, if it's not so evident to see it. This is a tube, 70 meters long. It's a cruise terminal. it's quite long, 70 meters, and it's about 3.8 meters high, so relatively low. The idea of this pentagon is to reduce the transversal moment in the section. And by doing that, we can open the site. And we don't need stiffness here, so this is quite magical when you see that, because first you don't understand, but you have only shear that, and you have a very small bending moment in the other direction. This pentagonal shape, you use it also in a timber bridge in CLT, in Zurich. And you see also now that the bridges are becoming larger and larger. We are now at 5 meters. We started at 3 meters, and we will see the next bridge 7 meters. So the width of the bridge are increasing due to the traffic, or the bicycle traffic, which is more intense. This is the inside of the bridge, done with CLT fully. This is during construction. It's not installed yet. It is foreseen to install it in 22 September, so in 3 weeks. Another strategy to find height, because what is a bridge? It's a materialization of height. It's nothing else, so forget all the rest. Is to work with 2 planes, 2 directions of 45 degrees. And this gives us the possibility, yes, to be higher, but also to be lower, and to find a structural height by playing on these 2 lines. And when we are doing that, the result can be, maybe I like this drawing, not because I've done it, but because it's really, all the information of the bridge are here. And this is quite important. Also, when you have something complex, you should have something very simple you can communicate with. And before you are going in all this grasshopper stuff and things, I think it's very important to have a clear idea of how you will draw it, but also how you will build it. And this simple rule of these 2 lines gives a very, finally very organic shape, something which is quite astonishing with these 2 parameters only. It's a Poissy, it's in France, over the Seine. It's also a historical site. You see that it will be on a location where a bridge existed about now 1,000 years before it was bombed in 1944. Yes, not by the German. Well, we are hoping to start this end of next year, the building, so it took a long time to get the process through. Again, a very flat bridge. This is a bridge now which was inaugurated a few weeks ago. It's in Belgium, and here we have even a smaller height to length ratio of 1 to 25. So again, it's sort of hybrid between a beam and a bowstring. It's the same strategy, 45 degrees, and we are working with that to get down also on the abutment and to bring the forces down to the ground. 7 meters here, so it's quite a big bridge for a pedestrian and cycling bridge. Well, that's my flying bridge, so I'm quite happy. And some photo. I don't have a professional photo because it's really a recent project. You see here how the efforts are going down to the ground on the 45 and transforming in an arch. From structure point of view, it's also a Virendeel, because we have to take asymmetrical effort. So these hangers here, these hangers here are also working as Virendeel to give enough stiffness. Some photos I got today, because yesterday someone made some photos of the lightning. And maybe I want to say something about this. We make bridges for the user. So the user experience is one of the focus. We are all talking about structure, but finally we are building for the users, for the people which are passing every day. And it's quite important that here we have a positive user experience, a quality, and equality also on different scales, because the man or the woman who gets over, he's in touch with the details. It's another scale than a bridge in the landscape. And that's quite difficult to have equality on these two levels, to enjoy the going through, having the view from the beach, but also enjoying the view from the shore to the bridge. Now we are going to Japan, and maybe you don't see what I want to show, but so I want to show this canopy. Well, it's 80 meters, and the idea was to have something very flat. So this canopy, it's this tetrahedral. It's an Euclidean volume. And when you look at this, you have two lines at 90 degrees. Of course, you can stretch this, okay? But you still get this volume and height. And finally, you can get to something very, very flat with one edge, which is very thin. Simple form at the beginning. It's like putting your two hands one on the other. So you create a volume with a line here and a line here. And we use this principle to get to make this canopy. And to give some texture, because we could not weld inside, you see how thick it is. We weld it outside, and it gives us texture. It tells something over how it was constructed. Well, and the last project, here it's in Tokyo, and we put some of these elements together to have this canopy of about 70 meters, 7 meters span here. Have to go quicker. With this very, very sharp edge again, and the feeling that it is really flying above. Difficult to understand how it is made when you are looking at. Voilà. And finally, we did several bridges there on this plaque. And I will talk a little bit of deck number 2, which is a sort of continuity of the origami building you are finding inside. It has been designed by the OMR. And the idea was to continue this. So we had a dialogue of how we could bring this outside and pass from one side to the other. This was an early model of the bridge. And this is the construction, which again looks very simple, but a lot of discussion to get to this result. Now it is finished, but again, we will have photo, I think, end of this year of this special bridge. Thank you a lot.